and welcome. My name is Mrs. Leslie, and today I'm going to be discussing permutations and combinations with you. Really, we'll end up focusing in this video in part 1 on permutations, but I will introduce both the definitions and some examples and some ways to go about solving. I will solve permutations in this one, and then go ahead and solve some combinations in part 2, so watch for that as well as an additional video. Permutations are arrangements in which order is important. For example, how many ways can a president and vice president be selected in a class of 25 students? In this situation, order is important because selecting the president and then vice president, if I start changing the order, it would be another outcome. I can use some students' names as examples. Let's say I have Brian and Elizabeth, and Brian is president and vice president is Elizabeth. If I switch their names around, it is a new outcome because then Elizabeth ends up being president and Brian ends up being vice president. Therefore, in this problem, order would be important and needs to be taken into consideration. There are 3 ways to actually solve these examples of permutations. One is listing. Personally, not one of my favorites because it is very easy to leave something out or double, count something. The counting principle, which in my opinion is actually the way to go. The counting principle I'll circle here is going to be the way we focus on solving problems that are permutations. There is also a formula. Again, the formula is a nice way to solve, but there are some restrictions with the formula and some situations where the formula is not able to be used and applied exactly the way it is. So again, the counting principle, in my opinion, is the best and the way we will end up working. Combinations are arrangements in which order is not important, so that's the opposite of permutation, and an example is one way we can look at that. How many 2-person committees can be chosen from a group of 7? And in this case, it is not important the order we state people's names within the committee. For example, again, I'll use students' names. We have, let's say John and Kaylee. And Kaylee and John are both part of the committee. If I say John and Kaylee are part of the committee, those are both the same committee. Nothing's changed. They don't have specific positions in the committee, so the order I say their names are not important, and in that case, it does not present another outcome. So in solving this, we can actually solve by either listing or a formula. Listing, again, you know how I feel from the beginning of the conversation, not exactly the best way in my opinion. It's a short list, but it's still easy to leave something out or double count something. My personal opinion here is the formula is the best way to go. And when we get to a more in-detail discussion on combinations in video part 2 of this, in that case, I will go into the formula, discussing how to use it, and all of the ways to solve and identify combination types of problems. So at this point, what I'd like to do is I would actually like to go ahead and maybe solve some problems. I'll move this out of the way. And so here we have a permutation problem, and we'll start with those types of problems. And all of these you'll want to watch for the fact that order does make a difference. In this problem, we will be finding out how many ways can the letters in the word modestly be arranged. And so we are trying to take these 8 letters, and we are just trying to rearrange them in different orders. So yes, order is absolutely important. We are arranging all of the letters in this word, and so in that case, we have 8 positions to fill. Let's get our pen. And so we have 1, 2, 3, 4, 5, 6, 7, and 8. And so now, in the 8 possible outcomes, and we have the 8 possible positions, we have in the first position, 8 possible choices of letters. We can use the M, the O, the D, the E, the S, the T, the L, the Y, and so there are 8 choices for the first position. Now, if we are just trying to arrange these letters specifically, we're not going to allow for any repetition, and therefore Next time we try to place the letter in the second position, we only have 7 to choose from. We've used 2, now we have 6, and each time it's going to decrease by 1 letter in order to use all letters once in the arrangement. If I was to multiply this, in this case, I would end up with we would end up with the answer of 40,000. Oh, and the pen, sorry about that. 40,320 would be our answer if we multiplied this out. So you've placed all of your positions, how many choices you have for each position within, and then use the counting principle and multiply. Let's see another example. We have 6 people that walk into a fast food restaurant at the same time. How many different ways can the first 3 be served? So in this case, we have a problem where 6 people are walking in. We want to know the order of the first 3 people being served. So we are only going to have 3 positions to fill here. The person that is served first, the person that is served second, and the person that is served third. In this case, the number of people that could potentially be served first are 6, because there are 6 people that walked in. If the first person then served, we're down to 5 people to serve in the second one, and 4 in the third. And so in this case, if we multiply here, we end up with 120 possible outcomes of ways that people could be served. Well, 3 people could be served, I should say. Let's actually do one more. In this problem, we want to know how many 6-digit numbers can be created from the digits 2, 5, 1, 9, 4, and 7 without repeating any. So we do have to be careful with that. If there is repetition or not repetition allowed, that will affect our setup of our problem. In this case, we have 6-digit numbers we want to create, so we're going to have 6 positions we are going to fill. We have the numbers 2, 5, 1, 9, 4, and 7. So we have 6 numbers we want to place within these, and we're not allowing for repeating. So in the first position, we have 6 potential numbers we could place. We're not allowing for repeating, so now that's going to decrease by 1 each time. And so our answer would be 720. One quick little side note, just in case this problem did allow repeating. If that's the case, and we've solved this problem the way it stands, but if we allowed repeating, in that case, every one of these 6 positions, we would have 6 choices. And so you'd see a situation where you'd be able to multiply 6 times 6 times 6 times 6 times 6 times 6. And again, that's simply because we could repeat, so we do not lose numbers as we place them. I hope that helps. That's part 1 involving permutations examples, and we will continue with part 2 when we work on, or where you see working on combination problems using the formula. Thank you.